Good morning. So many thanks for your time. We are deployed. So in 2015, we said we would have our first deployments. We had them. In 2016, we are only in the beginning of the year. We are beginning of March. We see extremely strong start, huge deployments that have been recently won. So these deployments are covering any aspect of IP networking, data center, large-scale aggregation, and the core. We have deployments across all the markets, large enterprise, service provider, web market. So really great adoption and extremely fast velocity. The first presentation on this internally at Cisco was in October 2013. So October 2013. So it very quickly adopted. So the agenda for today is detailed use case. So I'll go detailed advanced use case to show you what are the designs we are discussing with operators and the technology that goes with it. Everything I'm going to describe is shipping this year, is already shipping or will ship this year. Everything can be seen at the booth. There were many people going at the booth. I really encourage you to go to the booth to see the demonstration of all this because it's concrete. It's either shipping or will ship this year. First use case, inter-domain policy at scale. So I take two data centers that I'm going to interconnect with two metros and a core. I'm going to use a homogeneous sRGB. We always recommend this. I'm going to use a small one. In our implementation, you could use a much bigger one, but I'm just going to use a small one to show the scaling potential. This design, you see it in a large-scale aggregation, but we use it as well in massive-scale data centers, where we interconnect with this idea tens of millions of physical endpoints. So this is the goal for this first small sRGB, to show you the potential so that you get the idea. I'm going to use an sRGB of, for example, 16,000 to 24,000. I'm going to give the 16,000 range to the WAN. I'm going to give the 17,000 range to one of the metro, the 18,000 range to another metro, and then to show you the scaling potential, I'm going to use the same range, 20,000 to 24,000, for each data center. And I'll explain how we can get global identification with this sharing. In each of the islands, I am going to run in the metros islands, and in the core, I am going to use an independent ISS or SPF routing protocol with the segment routing extension. We are shipping this since June 2014. There has been numerous presentations on this. It is deployed. The benefits have been explained. It's the incremental deployment and the seamless interworking with LDP, so you can deploy this very quickly. So it's well known by this time. I highlight that each of these islands are independent. Then in the data center, we use BGP segment routing. So we have two implementations of this in our product portfolio, either on the Nexus hardware with the XE software or the NCS 5K with the XR software. So I have multiple options for you to deploy BGP-based segment routing in the data centers. Then from an inter-domain routing viewpoint, I am not going to use BGP inter-domain routing. Each of these islands are independent by design. I am going to redistribute only very small routes. It's only the one edge, so we call them aggregation in this design. We are going to redistribute the aggregation routers, so the borders of the core, inside the metro, and then from the metro down to the data center. We are not redistributing anything else. So with this, you have no connectivity from data center to data center. How are we going to give this connectivity? We introduced the segment routing PC. The segment routing PC has two components, a multi-domain topology that is fed real-time by BGPLS update from each of the domains. Then we have a compute block. Here we have the outcome of 3 years of research from a mathematical viewpoint to basically redesign all the traffic engineering algorithmic from scratch for segment routing. I don't have the time, but I really encourage you to understand the difference between doing traffic engineering with segment routing versus traffic engineering for Fremley, ATM, RSVPT. These are not the same algorithm. You have to redefine them from scratch if you want to use the full power of segment routing. So this is what the segment routing PC is. So from a service provisioning viewpoint, we use anything that is classical, layer 3 VPN, EVPN, etc. So the rightmost PE here is going to send a layer 3 VPN route with a VPN label and a next hop that is himself. The leftmost P is going to learn it. And here is the big question. He received the VPN route, but he doesn't know where this next hop is because it's in another domain and everything is isolated. How do we resolve this? We resolve this with what we call on-demand segment routing next hop, ODN. So when the leftmost VP receives the VPN route for a next hop he doesn't know about, the ODN feature in the router kicks in and says, well, I don't know where this is. I need to get that next hop. So he sends a PSEP request to the segment routing PCE server, and there he has the multi-topology database. He has a segment routing algorithms. So the SRPC simply compute a path to go from the leftmost PE to the rightmost PE. And that's very easy to do because it's basically take the longest hop you can take up to a 1H border router. So it's 16,002. It's the furthest reachable one aggregation router. Then you take a hop to 18,001, which is your DCI to the data center where you want to go. And once you are in the data center where you want to go, you use the global label 20,001, which is the global label, assign it to the remote PE where you need to go. And note well that the leftmost PE and the rightmost PE are the same global label. They are both 20,001. You don't need to do it that way. But if you want to have massive scaling of tens of millions of physical endpoints, then you need more than 1 million labels. And it's to explain that you can reuse these labels. Why? Because once you are at 18,001, the rightmost DCI, it's obvious 20,001 is inside that data center. It's the rightmost PE. So we have just explained how we can get on-demand next hop reachability through an inter-domain segment routing fabric that is otherwise disconnected. But the use case is about policy at scale and simplicity. So that's really the policy that is interesting us. Now I redo exactly the same use case, but the rightmost P is going to advertise a VPN route, EVPN, etc., but he simply tags it with a community. And that community means an SLA contract. It travels through the route reflectors, the leftmost PE gets it, and the leftmost PE, the ODN feature kicks in, and he says, well, first, I don't know this next hop, but even more, there's an SLA contract attached to it. I cannot resolve this. So I asked the segment routing PC. The segment routing PC, it's very easy for it. He has a multi-domain topology view of the network. He knows what is the SLA contract. So he knows, let's say it's a low latency optimization. We have all the algorithm we have developed specifically for segment routing. And he's basically computing, well, low latency end-to-end data center to data center, you really cannot go all the way to that one AG router. You need to enter the one there. And then in the one, you need to take that specific hop in order to get the low latency path. Then you need to exit from the one at that specific DCI to get the low latency path. Once you are in a target metro, typically there's no longer any latency differentiation. You then go to the DCI and then to the data center. So basically, he expressed it with a list of segments, and he replied to the VP. The VP received the list of segments, install it in the data plane, and then installs the BGP routes directly on this segment routing policy. So it means that you have achieved inter-domain SLA with scale and simplicity. Why inter-domain? We cross the domains. SLAs, you've seen it. We attach policies to each of the VPN routes. Why do we say at scale? Because the people doing this, they are doing this for 50,000 access nodes aggregation, so 50 metros across an international network. You know very well when you do these designs that any access device talks with very few other access devices. So it's very important to have something that where you populate the routes only on demand for the services that you really need. Why simplicity? Well, why simplicity? Because there's no RSVP, there's no midpoint state, there is no tunnel. With segment routing, we have started from scratch. We do not import anything from previous traffic engineering development. We have no tunnel. We have no concept of classification into tunnels, etc. Here, everything is automated. You send a BGP route, you tag it with an SLA. The incoming PE recognizes that either he can compute himself or not. He asks the segment routing PC, and then he puts the BGP routes onto the policy. You don't need to configure anything. Seamless transition. Everything in segment routing as we designed it is for seamless transition. So we know that most of these networks already exist, and we know that already they have BGP for interdomain routing between these domains. So obviously we support it. So you can look at the purple plane as the existing interdomain routing to unite these islands. And then on the bottom, you introduce your segment routing PC. We designed the ODN feature on the router such that when you receive a VPN route, if there is no SLA contract associated to it, if he has a route to the next hop in the BGP interdomain routing, he uses it. So it's basically using the existing brownfield deployment. But if you receive a VPN route with an SLA contract, well, everybody knows that BGP 3107 interdomain routing only gives you best effort routing. There's no SLA with BGP interdomain routing. So ODN then says, well, that's not enough. It's a best effort path. This is not what I need. And then he kicks in and he asks the segment routing PC. So you can completely introduce this in Ship in the Night, only do it for some new services, premium added value, and once you get used to it, maybe some of you will remove BGP interdomain routing. But that's not our goal. Our goal is to deliver the policy at scale with simplicity. I encourage you to go to the booth because this technology, you'll see it in action for different use cases that otherwise I think were not possible to do, although they are so obvious from a business viewpoint. So the service orchestration comes at the leftmost VPE, and he orchestrates their service, which is a pseudo-wire, to a rightmost PE in the data center. And when the service orchestration comes in, it says, it puts the SLA contract, and it says it has to be primary backup, path protection, failover. And that's the only thing the service orchestration NSO, the tail-F acquisition, does. Once the VPE has this, the ODN feature kicks in and it says, ooh, I need two primary backup paths, disjoint, interdomain, I cannot compute this. He has the segment routing PC, he gets two lists of segments, he installs that in the data plane, and then he runs SBFD on each of the paths to track the availability, and then he does path protection. Everything is automated, and it's at the booth. It will ship this summer. Another demonstration you can see, service orchestration comes to two different PEs to orchestrate them to create a pseudo-wires to two different remote PEs. These leftmost PEs are provisioned with an SLA contract that says you must be disjoint from another pseudo-wire. Each PE has no way to compute this because he doesn't know the path of the other one and he doesn't know the interdomain topology. So again, ODN kicks in, asks the request, the segment routing PC sees the two requests, he computes two disjoint paths end-to-end. Again, at the booth, it's shipping this summer. Binding seat. Binding seat is in the segment routing architecture since day one. Since day one, it is in the architecture. We've been shipping it for a long time. What is it? If you have an intermediate policy, like the purple policy here, which goes from an entry point to the WAN to a DCI between the rightmost, the right metro and the right data center. And this policy implements a low latency path through the WAN, through the metro, up to that data center. And it is implemented, let's say, with 4 segments. Every time we install a policy anywhere, the head end of that policy binds to it what is called a binding segment. This is a local label that represents the steering into that policy. This is installed in the data plane in order to allow for hierarchical steering. All the time when we do this, we advertise via BGPLS or via PSEP notification the availability of this intermediate policy and its binding segments. So the segment routing PC knows about it. So when the leftmost PE asks a request with ODN to say, hey, I need low latency to the rightmost PE, the segment routing PC is intelligent. It computes a path using the intermediate policies. And so he replies not a long list of segments, but he replies only 3 segments. From where you go, from where you are, he says, take a hop to AG1, which is the entry point to the WAN. Then use the binding segment 4001. Get into the purple policy that will allow you to travel the WAN and the right metro up to the DCI, at which point 20001 is the VPE where you need to go to. So this is obvious. Nothing new needs to be defined. That's in the architecture, and we've been shipping it for quite a time. The segment routing PC is not a God box. We have designed it as in a deployment model that is like RAD reflectors. Think about them like in pairs that you deploy per service, per geography. And if you need to have more compute capability, you add units in each of the, let's say, tuple. It becomes a 3-tuple, etc. The segment routing PC functionality we have is the same exact code as we have on the router. It's simply populated with a bigger database. But all the algorithms we have developed are either for the router to compute for himself or for the router to compute in a multi-domain case. It means that you can think about them just like RAD reflectors. You enable the segment routing PC, for example, on your aggregation routers. But then if you want also to virtualize them, you take virtualized units in the data center running on x86, shipping this summer as well. Who can do more can do less. Everything I explained is in the context of inter-domain routing. But for some of you, you run an enterprise, you run a smaller ISP, you'd like to do this in a single domain. And that's this use case that I would like to highlight. So here, I have a single domain, so ISIS level, single level, or SPF single area covering the world. And I have point of presence in Brussels and in Tokyo. Tokyo is 16,003, and Tokyo advertised 2 routes. 2 VPN routes, YY, which is a VPN route which is low cost, and XX, a VPN route that needs low latency path. They are going to be tagged with these SLA contracts, the extended communities. Everybody knows that when you run an ISIS OSPF network, you optimize the metric for one objective. Let's assume that the ISIS OSPF metrics are optimized for low cost. It means that for Brussels to go to Tokyo, the path will be via US, because this is where the capacity is cheaper. But from a low latency viewpoint, going via US is crazy. You want to go via the Russian site, which is more expensive but better from a latency viewpoint. How can we achieve this? Exactly the same as before. Tokyo is going simply to tag the VPN route XX with an extended community that says low latency. It goes through the RAD reflector, Brussels receives it, and the ODN feature kicks in. It says, ooh, I receive a VPN route from Tokyo. Tokyo, I know, it's in ISIS. But Tokyo low latency, I don't know, it's not ISIS. So he kicks in, but either here, instead of asking the segment routing PC, he basically compute himself. Because that's what I said. All our algorithmic is implemented on the router in the same way as the segment routing PC. It's the same code. And so he computes for himself, and on demand, he creates, well, how can I go from Brussels to Tokyo low latency? I need to go via Russia. OK, I take a hop in Moscow, then I take a hop in Tokyo. I install it in my data plane, and then I install my BGP route on it. No tunnel to configure, no RSVPT, no midpoint, no signaling. Extremely simple. No PBR tags, neither in terms of classification, no in performance. So it's just, I think, obvious to do it that way. So that's it for policy at scale with simplicity. Now, quickly, a few other use cases. Topology-independent LFA. As Bruno mentioned, we have presented on this at previous conferences. Stefan gave very detailed presentation to show the benefits of topology-independent LFA. These benefits are the 50 millisecond protection, the simplicity to operate and understand, because it's automatically computed by ISIS OSPF. Once again, a lot of research that comes to an implementation of a complete solution that works in any case mathematically proven, but the complexity is digested by the implementation in the router. 100% coverage, predictable, because it's the optimum backup path. It's the post-convergence path. And as Stefan proved when he did his presentation at the last conference, it supports incremental deployment and is applicable to LDP and IP traffic, not only for segment routing. So, Clarence, why do you talk about this? For us, we're shipping this for 18 months. It's deployed. So where is the novelty? The novelty is that we have node protection and we have SRLG protection. It's at the booth. You can play with it. It's shipping this summer. As some of the operators have said, well, there's no longer any requirement. If you have any new requirement, let us know. But basically, link protection, node protection, SRLG protection, any topology mathematically proven, the optimum backup path, because it's the bus convergence path, I think the problem is closed. Microloop avoidance. Microloop is a problem of IP since day one. 1 to 5, when 4, 5 is up, is the green path because there's a very bad cost on the link 6, 5. If the link 4, 5 goes down, depending on when the routers are going to update the routing table, there will be transient loop. If 1 updates the table before 8, if 8 updates the table before 7, transient loops will occur. These are called microloops. This is a drawback of IP since day one. It's the nature of IP hop-by-hop routing, independent convergence. As always, we work very closely with operators, and so Stefan is going to go in 20 minutes in much more details on this. I'm just introducing this, but basically the code is at the booth. You can look at the demonstration. It will ship this year. It's mathematically proven. We solve any microloop, not only local, but as well remote, for link up, link down, metric increase, metric decrease. Again, a lot of mathematical research and an implementation in the code. So Stefan had an early code of the drop, and he will do a bit more update on how it works. Again, the simplicity, this is only one line of comments. Microloop, avoidance, segment routing, and then you get the outcome of the mathematical research. SRv6, since day one, I designed the segment routing architecture for IP. I'm just using MPLS data plane for its convenience, for its availability, but this is an IP-based architecture. Everything is done for IP. So all the control plane you have seen, topology-independent LFA, link node SRLG protection, microloop avoidance, segment routing T, ODN, segment routing TPC, 3 years ago, we knew what we wanted to do, and we have done everything to be reusable for IP. What we needed to do for IP is to enable the data plane to support the segment routing extension header in the data plane for IPv6, to be able to use segment routing also for the IPv6 pure data plane. So what we want to announce is on top of ODN, the segment routing PC, the topology independent LFA for node, SRLG protection, the microloop avoidance, yet the new novelty of this year is that segment routing v6 in hardware is available. So if you want to go at the booth to see the demonstration, if you want to know much more about it, please talk to us. There's a huge applicability. John Lady at Comcast, once again, we always work close to the operators to be real on explicit use case. It's going to take 20 minutes to walk through his use case. I think they are really applicable to many of you. It's only the top of the iceberg. There's much more to do. And I really encourage you to listen to that presentation. Conclusion, we really believe that segment routing is the fundamental architecture for modern IP network. The goal we seek is to provide a unified fabric with policy through data center, metro, and WAN. We want to unify the fabric. We offer functionality that has never seen before. The topology-independent LFA, the ODN functionality, the microloop avoidance are only small examples of all what we resolved that was not resolved before. And they are resolved by mathematical analysis and proof that are then coded into the code in order to get the simplicity. Why do we get the simplicity? It's not by making dumb things. It's because we make the simplicity by having a lot of research that is then into automation of the intelligence in the code. We have done all of this with removal of protocol. We have removed LDP that was redundant by birth, and we have removed RSVP that was proven to be way too complex to operate and not scalable. So we have not added any protocol. We're just focusing on ISIS, OSPF, and BGP and PSEP. That's the only thing we use, and few lightweight extensions. And then we use these building blocks, I think, in the right way. Since the beginning, we have a strong operator endorsement. We reached quite quickly the multi-vendor consensus, and as I said, impressive deployments in terms of width, applicability across markets, and velocity. Many thanks for your time.
Thank you, Clarence. We have time for questions. Any questions for this first presentation? We have Clarence for an overview of segment routing.
Thank you.
No question? Okay. Thank you, Clarence.
Thanks.
Next speaker is Stefan Litovsky from Orange. Stefan Litovsky is a network